From the gentle pirouette of a falling leaf to the unseen, furious gyration of the atom, our universe is caught in a ceaseless dance. It is a cosmos of movement, a symphony of rotation. We see it in the water spiraling down a drain, the phenomenon mirrored in the colossal storms that rage across the surfaces of distant gas giants. We feel it in the turning of our own world, the steady, reliable rotation that gives us the rhythm of day and night. But is this merely a series of isolated coincidences, a collection of unrelated motions, or is it a clue, a whisper of a fundamental truth woven into the very fabric of reality? The evidence surrounds us, from the most minuscule scales to the most incomprehensible. Everything, it seems, is spinning. The question is not what, but why. Why? This universal, relentless, and beautiful compulsion to turn? The answer is not found in a single place, but is scattered across the entire 14 billion year history of time. It begins with a law of physics so fundamental, so elegant, that it governs the fate of dust clouds and the death of stars. This principle is known as the conservation of angular momentum. It is a rule as unbreakable as gravity, as certain as the passage of time. To truly comprehend its cosmic power, we need not look to the heavens, but to a place far more familiar. Imagine an ice skater poised at the center of a vast frozen stage. She begins. Her spins slowly, her arms outstretched, reaching wide as if to embrace the entire auditorium. Her rotation is graceful, measured, and controlled. Her mass is distributed over a wide area. Then, with a sudden fluid motion, she draws her arms inward, pulling them tightly against her body. The transformation is instantaneous and breathtaking. Her spin accelerates dramatically, becoming a blur of motion, a vortex of human form. She has not pushed off the ice again. No external force has been applied to speed her up. The energy for this astonishing acceleration came from within the system itself. The total amount of her spin, energy, her angular momentum had to remain constant. It is a conserved quantity. When her arms were outstretched, her mass was spread out, and that fixed amount of angular momentum translated into a slow spin. By pulling her mass in towards the central axis of rotation, the Messrs' universe demanded a cosmic rebalancing. To keep the total angular momentum the same, her rotational speed had to increase. This is the law in its most elegant form. For a closed system with no external twisting forces, the total angular momentum can never change. It can be redistributed, but it can never be created or destroyed. Now, take this simple, beautiful image of the skater and project it onto the grandest stage imaginable, the universe itself. The story of cosmic spin begins in the unimaginable furnace of the Big Bang. In the first fleeting moments after its birth, the universe was not a place of structure and form. It was a seething, incandescent, and almost perfectly uniform soup of elementary particles and energy, expanding at an incredible rate. The key word here is almost. If the early universe had been absolutely mathematically perfect in its smoothness, with every particle's energy and density identical to its neighbors, gravity would have pulled evenly in all directions. No structures would have ever formed. We would not be here. But the primordial cosmos was not perfect. On the smallest, quantum level, it was a frothing sea of uncertainty. Tiny, random fluctuations in energy and density rippled through the fabric of space-time. These were unimaginably small variations, like microscopic imperfections on a colossal, polished sphere. In this chaotic environment, the particles were not all moving in perfect straight lines away from the center. They jostled, they collided, they moved past each other with tiny, random, off-center gravitational tugs. Imagine two clouds of primordial gas drifting through the early five, cosmos. They are drawn together by their mutual gravity. If one passes slightly to the side of the other's center of mass, gravity will not just pull it inward, it will pull it into a curve. This slight nudge, this infinitesimal gravitational torque, imparts a tiny amount of rotation to the system. A minute measure of angular momentum is born. In the beginning, these rotations were negligible, microscopic eddies in a vast and expanding ocean. But the universe had all the time in the 30 world, and it had the ice skater's secret. Millions of years passed. The universe continued to expand and, crucially, to cool. This cooling allowed gravity, the patient sculptor of the cosmos, to begin its work. Throughout the void, vast, ethereal clouds of hydrogen and helium gas, hundreds of light years across, began to feel their own weight. These were the great nebulae, the stellar nurseries. Each of these colossal clouds, born from the initial chaos, carried within it some small residual amount of net rotation, the sum of all those tiny nudges from the dawn of time. At first, this spin was imperceptibly slow, perhaps one full rotation over millions of years. But gravity is relentless. It began to pull these clouds inward. Slowly, inexorably, over eons, the diffuse gas began to contract, collapsing down towards its own center of mass. And now, the ice skater takes the stage, as the cloud, once spanning light years, shrank to a fraction of its former size. Its mass was pulled closer and closer to the center of rotation. To conserve its primordial, angular momentum, the cloud had to spin faster and faster and faster. The contraction did not form a simple, shrinking sphere. The newfound rotational energy created an outward force, strongest at the cloud's equator. This force resisted the inward pull of gravity along the equatorial plane, but not at the poles. The result was a dramatic flattening. The collapsing sphere of gas transformed into a vast, spinning, flattened structure. It became a cosmic potter's wheel, a swirling platter of gas and dust that we call an accretion disk. At its center, the material became ever more compressed, ever hotter. The pressure and temperature grew to unimaginable levels until a point of ignition was reached. Deep within the heart of the spinning disk, nuclear fusion began. A star was born. This process, this gravitational collapse governed by the conservation of angular momentum, is the reason our own sun rotates. It completes a full turn roughly, once every 27 Earth days, a lingering memory of the ancient spin of the nebula from which it was formed. But the story does not end with the star. The accretion disk, the vast, swirling remnant of the collapsed cloud, was the cradle for everything else. This protoplanetary disk was a cosmic blizzard of gas, dust, and ice, all orbiting the newborn star in the same direction, a direct inheritance from the parent cloud's primordial rotation. Within this turbulent, spinning disk, a new chapter of creation unfolded. Tiny grains of dust and ice began to stick together through electrostatic forces, like dust bunnies forming under a bed. These small clumps grew into pebbles, the pebbles into boulders. These larger bodies, now with significant gravity of their own, swept through the disk, accumulating more and more material. They became planetesimals, the building blocks of planets, kilometers across. These planetesimals continued to collide and merge in a chaotic, violent dance that lasted for millions of years. Each collision was rarely a perfect, head-on impact. More often, they were glancing blows, off-center strikes that added yet more spin to the growing protoplanets. This is why virtually every planet and asteroid in our solar system not only orbits the Sun in the same direction but also spins on its own axis. The Earth's 24-hour day is a direct consequence of this ancient history of chaotic, spinning assembly. Our moon, too, was likely born from spin, the result of a cataclysmic off-center collision between the young Earth and a Mars-sized protoplanet named Theia. The debris from this impact was thrown into orbit, eventually coalescing into our lunar companion, forever locked in a tidal dance with its parent world. Even the exceptions tell the same story. Venus rotates backward, a slow, retrograde spin that is still a subject of intense study. Perhaps a massive, late-stage impact effectively reversed its original rotation. Uranus is tipped over on its side, spinning almost perpendicularly to the plane of the solar system, another likely scar from a titanic collision in its distant past. These anomalies are not violations of the rule, they are testaments to the violent dynamic nature of formation within a spinning disk, where angular momentum is not just conserved but violently redistributed. The same principles that build solar systems also build in the grandest structures in the cosmos, the galaxies. On an even a larger scale, the primordial universe contained vast filaments of gas and mysterious dark matter, the invisible scaffolding of the cosmos. Where these filaments intersected, immense clouds of material began to collapse under their own gravity. Just like their smaller stellar nursery cousins, these protogalactic clouds possessed a small, net angular momentum from the universe's imperfect beginnings. As these colossal structures, containing the mass of hundreds of billions of suns, began to contract, the ice skater effect took hold on a mind-boggling scale. The clouds spun faster and faster, flattening into an enormous disk of stars and gas. This is the origin of the magnificent spiral galaxies that pepper our night sky. When we look at an image of the Andromeda Galaxy, our closest large neighbor, we are not just seeing a static collection of stars, we are witnessing a snapshot of a dynamic, whirling system, a celestial whirlpool 200,000 light-years across. Every one of its trillion stars is caught in a majestic orbital dance, a gravitational ballet choreographed by the conservation of angular momentum over 13 billion years. Our own Milky Way is such a structure. Our Sun, along with its family of planets, is located in one of its spiral arms, completing a grand tour of the galactic center once every 230 million, 2 years. We are all passengers on a spinning planet, orbiting a spinning star inside a spinning galaxy. The rotation is nested, layer upon layer, an inheritance passed down from the dawn of time. The study of galactic rotation led to one of the most profound discoveries in modern science. In the 1970s, astronomer Vera Rubin was meticulously measuring the speeds of stars at various distances from the centers of galaxies. She expected to find what we see in our solar system. Objects farther out move more slowly. Mercury zips around the Sun, while distant Neptune plods along. Gravity's pull weakens with distance, so orbital speed should decrease. But Rubin found something utterly baffling. The stars on the outer edges of the galaxies she observed were moving just as fast as the stars closer in. In fact, the entire galaxy seemed to be rotating like a solid disk, a cosmic pinwheel. This should have been impossible. The visible matter, the stars, gas, and dust could not provide enough gravity to hold on to these fast-moving outer stars. By all rights, they should have been flung off into intergalactic space. The only way to explain this observation was to conclude that the galaxy was embedded in a vast, invisible halo of some other kind of substance, a material that does not interact with light but exerts a powerful gravitational pull. This mysterious substance was named dark matter. The spinning of galaxies a direct result of conserved angular momentum, became the primary evidence for the existence of an invisible universe, a hidden cosmos that outweighs all the visible matter we can see by a factor of more than 5 to 1. The dance itself revealed the presence of an unseen partner, and as we look closer at the universe, we find that the law of spin leads to even more extreme and bizarre phenomena. When a truly massive star, many times the mass of our Sun, reaches the end of its life, it does not fade away gently. It dies in a spectacular explosion known as a supernova, one of the most de-energetic events in the universe. For a brief period, it can outshine its entire host galaxy. While the outer layers blasted into space, the star's core undergoes a catastrophic gravitational collapse. This core, containing more mass than our entire Sun, is crushed down into an object only about 20 kilometers across the size of a city. It becomes a neutron star, a sphere of matter so dense that a single teaspoon of it would weigh billions of tons. Here, we witness the ice skater's finale in its most extreme form. A star that might have rotated once every few weeks, now compressed to an infinitesimal fraction of its former size, must spin at unimaginable speeds to conserve its angular momentum. Many of these neutron stars rotate hundreds of times every single second. They possess incredibly powerful magnetic fields, which channel beams of radiation out from their magnetic poles. As the star spins, these beams sweep through space like a cosmic lighthouse. If one of these beams happens to sweep past Earth, our radio telescopes detect a regular pulsing signal. For this reason, these rapidly spinning neutron stars are known as pulsars, the universe's most precise clocks. Their incredible rotation, a direct consequence of gravitational collapse. But there is a fate even more extreme than a neutron star. For the most massive stars of all, when the core collapses, gravity is so overwhelming that nothing can stop it. Not even the pressure of densely packed neutrons. The core continues to collapse indefinitely, crushing itself down to a point of infinite density, a singularity. It creates a region of space-time where gravity is so strong that nothing, not even light, can escape. It becomes a black hole, and just like the star from which it was born, a black hole retains the angular momentum of its parent. These are not just static gravitational sinkholes. They are spinning, dynamic objects. A rotating black hole, described by the mathematics of Roy Kerr, is a truly terrifying and wondrous thing. Its spin is so powerful, so extreme, that it doesn't just exist within space-time, it actively drags the very fabric of space-time around with it. This phenomenon is known as frame dragging. Imagine placing a heavy, spinning ball bearing into a vat of thick honey. As the fader ball spins, it would create a small whirlpool in the honey, immediately surrounding it. A rotating black hole does this too. The universe itself. Space and time are twisted into a vortex around the spinning singularity. Anything falling into this region, the ergosphere, is forced to rotate with the black hole. It is a place where it is physically impossible to stand still, because space itself is flowing like a river. This ultimate expression of rotation, a literal twisting of reality, is yet another echo of that tiny, initial asymmetry at the beginning of all things. From the grandest galactic structures to the most exotic stellar remnants, the story seems consistent. But does the principle hold at the absolute smallest scales? What happens when we venture into the quantum realm, the strange and counterintuitive world of subatomic particles? Here, the concept of spin takes on a new, even more fundamental meaning. Particles like electrons, protons, and neutrons possess a quantum mechanical property that we also call spin. It is crucial to understand that this is not a literal rotation. An electron is not a tiny, solid ball spinning on an axis. It is a point-like particle. Quantum spin is an intrinsic, fundamental property like mass or electric charge. It is simply part of what an electron times is asterisk. However, this intrinsic property behaves mathematically in exactly the same way as angular momentum. It has a magnitude, and it has a direction. This was first proven in the 1920s through the famous Stern-Gerlach experiment. Scientists fired a beam of silver atoms through a non-uniform magnetic field. If the atoms had no intrinsic angular, if they should have passed straight through. If they were, like tiny classical spinning tops, their random orientations would cause them to be deflected into a continuous smear on a detector screen. What they saw was astonishing. The beam split into two distinct, separate beams. This meant the quantum spin of the electron could only have two possible states, which we now call spin up and spin down. It was quantized. It could only take on discrete values, not a continuous range. This inherent quantized angular momentum is a foundational property of the matter that makes up our world, the stability of atoms, the rules of chemistry, the very existence of the periodic table of elements, all depend on the quantum spin of electrons. So, in a very real sense, the universe is not just spinning on the large scale. It is built from a foundation of fundamental particles that each carry their own irreducible, quantized form of angular momentum. We are left with a staggering and beautiful conclusion. The universe is in motion not by accident, but by its very nature. From the inherent quantum spin of the particles that form the building blocks of matter, to the off-center gravitational tugs in the primordial fog, a legacy of rotation was established at the moment of creation. This primordial angular momentum, a quantity that can never be lost, was passed down through the ages. It was concentrated and amplified by the patient, inexorable force of gravity. It shaped the collapsing clouds of gas into the spinning disks that would become cradles for stars and planets. It sculpted the galaxies into majestic, whirling pinwheels of light. It accelerated the collapsed cores of dead stars into the universe's fastest spinning objects, and it was preserved in the ultimate cosmic prisons, the rotating black holes that twist the fabric of reality itself. Every time we watch a figure skater accelerate into a blur, we are seeing a local demonstration of the same cosmic law that formed the Milky Way. The swirl of cream in a coffee cup is a distant, humble echo of the protoplanetary disk that gave birth to Earth. The spinning of a child's top is a faint reflection of the pulsar's frantic dance. The universe is not a static diorama. It is a dynamic, evolving, and creative entity. This universal spin is not just a feature, it is the engine of creation, the mechanism that allows for the formation of complex structures. Without it, there would be no flattened disks, no concentrated cores, no planets, no stars, and no galaxies. There would only be a cold, diffuse, and lifeless expanse of gas. The spin is the signature of a cosmos that is alive with possibility. It is the enduring rhythm of the cosmic dance, a dance that began with the Big Bang and has never, for one moment, stopped. And we are, all of us, fortunate enough to be part of its magnificent, unending choreography. What does it sound like when the universe screams, "Not a sound of air, for there is none in the void. Not a sound of matter, for the distances defy all echoes. This is a sound of a different order entirely. It is the sound of space itself being torn and twisted. It is the sound of time stuttering, stretching, and snapping back. A primordial percussion from an era we can barely comprehend, a cry of such impossible violence that it carries across billions of years, undiminished in its terrible silent majesty. To understand this sound, you have to witness its birth. You have to travel back, far back through the lonely corridors of cosmic history, to a time when the universe was younger, wilder, more densely packed. Here in the dim twilight of the cosmic dawn, galaxies were not serene islands of light. They were brawling adolescents, swarming and colliding in a gravitational mosh pit. Imagine two of them, two majestic spiral cities of 100 billion stars each drawn together by a force as patient as it is inexorable gravity. For 1 billion years they have been circling one another in a slow, hypnotic waltz. From a distance, it is an act of breathtaking celestial creation. Streams of stars are pulled loose like threads of silk, forming immense tidal tails that stretch for hundreds of thousands of light years. Vast clouds of interstellar gas and dust are compressed, shocked into life, igniting a firestorm of star formation that sets the merging galaxies ablaze with the fierce blue light of newborn suns. It is a spectacle of cosmic renewal, a canvas of stunning beauty. But this dance of light, this flurry of stellar birth, is merely a distraction. It is the gentle prelude to the real show, the beautiful shimmering veil drawn across an abyss of unimaginable power. The true conflict, the event that will define the fate of this new composite galaxy for all of eternity, is happening where you cannot see. It is unfolding in the darkness at the very heart of the storm. For at the center of each of these colliding galaxies there is a monster. A gravitational singularity, a point of infinite density, cloaked by an event horizon from which not even light can escape. These are not the stellar mass black holes born from the collapse of a single giant star. These are the titans, the governors of galaxies, the quiet kings on their thrones of darkness. They are supermassive black holes, and their masses are not measured in suns but in millions or even billions of suns. Each one is a cosmic anchor, its gravitational influence binding every star, every planet, every speck of dust in its galaxy into a coherent spinning whole. They are the dark hearts around which everything revolves, silent, ancient, and insatiably hungry. And now, as their host galaxies merge around them, these two dark hearts have finally found each other. Their celestial dance, once spanning millions of light years, has now shrunk to a frantic, intimate embrace. The stars that once separated them have been flung away by a gravitational slingshot of terrifying efficiency. The gas and dust that once clouded the galactic cores are now being funneled inwards, forming a swirling accretion disk of incandescent plasma. This disk, a vortex of matter heated to millions of degrees, shines with the light of 1 trillion suns. It is a quasar, a celestial blowtorch that outshines the combined light of all the stars in its own galaxy. It is the death scream of matter as it makes its final fatal plunge. Yet even this awesome display of energy is nothing. It is the flickering of a candle next to the nuclear furnace that is about to ignite. The two supermassive black holes are now alone, the last two dancers on a cosmic floor they themselves have cleared. They are now just light years apart, then light months, then light weeks. Their orbital speed approaches a meaningful fraction of the speed of light. They are carving through space-time, churning it like a ship's propellers in a cosmic ocean. The very fabric of the universe is being warped into a violent, spiraling vortex around them. From our perspective, time near these behemoths would be running unnervingly slow. A clock near the maelstrom would tick minutes, while our own ticked through centuries. They are two gravitational wells of infinite depth, spinning faster and faster, closer and closer. But here, they face a strange and confounding cosmic barrier. As they shed energy by flinging away nearby stars, their orbit shrinks. But as their orbital arena becomes empty, there is nothing left to interact with, nothing to shed that last critical bit of momentum. Theory suggests they could stall here, orbiting each other for billions of years at a distance of about 1 parsec, a cosmic standoff between two entities that can get no closer. This is the final parsec problem, a maddening puzzle for astrophysicists. How do these giants overcome this last gap? How do they make the final fatal plunge? Do they wait for another galaxy to fall in another star to wander too close? Or is there another force at play, something more fundamental, something that bleeds away their orbital energy directly into the structure of the cosmos itself there is, and it is the key to this entire story. The answer lies in the very nature of gravity as described by Einstein. Mass, he told us, does not create a force. It tells space-time how to curve, and space-time tells mass how to move. And when you have two objects with the mass of billions of suns spinning around each other at nearly the speed of light, they do not merely curve space-time, they whip it into a frenzy. They are generating waves, ripples in the geometry of the universe. Gravitational waves. These are not waves that travel times through time-space. They are waves times of time-space. As they radiate outwards, they carry with them colossal amounts of energy, bleeding it directly from the black hole's orbit. This is the solution to the final parsec problem. It is the universe's own mechanism for ensuring that what gravity has joined together nothing can put asunder. The gravitational waves become a relentless drain, a cosmic friction that seals their fate. The stall is broken. The final spiral begins. Now the pace accelerates into a terrifying crescendo. In the final minutes of their eons-long dance, they complete thousands of orbits. The space between them convulses. They are two spinning tops of pure warped geometry, and the distortions they create are no longer subtle. A gravitational wave passing through you right now from a distant event might stretch and squeeze your body by less than the width of a proton. You would never ever feel it. But here at the epicenter, space-time is no longer a stable stage. It is the lead actor in a violent drama. Space is being stretched and compressed by meters, then kilometers. The two event horizons, the one-way membranes that define the black holes, begin to distort. They are pulled into teardrop shapes, reaching for each other across the rapidly shrinking abyss. The frequency of the gravitational waves climbs, rising from a low thrum to a piercing chirp. It is the sound of the universe's two heaviest hammers about to strike the anvil of reality. And then it happens. The two horizons touch. For one fleeting, extraordinary moment, they form a single, contorted, dumbbell-shaped object, and in the next instant they merge. The two singularities, the 2 points of infinite density, plunge into each other and become one. The resulting object is a single, larger and violently vibrating supermassive black hole. In this final fraction of a second, an amount of energy is released that beggars all human description. The raw mass of several entire suns, perhaps as many as 100 million of them, is converted directly into pure gravitational energy. Think of the power of a supernova, the explosion that ends the life of a giant star, which for a few weeks can outshine an entire galaxy. This merger in its final moment releases more energy than all the stars in all the galaxies in the entire observable universe combined. Let that sink in for a moment. All the light from every star across every galaxy we can see is but a whisper compared to this. It is the single, loudest, most energetic event to occur anywhere in the cosmos since the Big Bang itself. And yet it happens in near total silence and darkness. No light is produced from the merger itself, only from the tortured disk of matter that will soon be consumed or flung away. The entire cataclysmic release of energy is invisible. It is a ghost of an explosion, a shout made of pure gravity. The newly formed black hole is not calm. It is a disturbed, misshapen entity. It rings, like a bell struck by a cosmic hammer. It wobbles and vibrates, shedding the last of its deformities and settling into a perfect sphere. This ring-down phase broadcasts a final, fading chorus of gravitational waves, a unique signature that encodes the precise mass and spin of the new monster it has become. The sound fades. The scream is over. A new, larger, dark heart now sits on the throne of a new, larger galaxy. A galaxy born of violence, forever scarred and shaped by this titanic union. The event is finished, but its message has just begun its journey. That blast of gravitational waves that ripple in the fabric of reality now travels outward in all directions at the speed of light. It is a perfect sphere of expanding information, a ghost of the cataclysm that created it. It passes through stars as if they were not there. It traverses entire galaxies, unaffected by their dust, their gas, or their gravity. It flies through the immense empty voids between the cosmic filaments, losing none of its integrity. It is a message in a bottle thrown into the cosmic ocean billions of years ago. a message written in the fundamental language of the universe, the curvature of space-time. For eons, it travels a silent testament to an ancient collision. It carries the story of how galaxies grow, how the largest structures in the universe are built from the wreckage of smaller ones. It holds the secrets of gravity in its most extreme and untested state, where Einstein's theories are pushed to their absolute breaking point. It is a fossil, an echo, a memory of a universe that no longer exists. And for all of human history, as we looked up at the skies, this wave and countless others like it have been washing over us, completely undetected. We were cosmic beings, born deaf and blind to the most profound events unfolding around us. Our telescopes, our eyes, are built to see light, to capture photons. They gave us a stunning but ultimately incomplete picture of the cosmos. It was like trying to understand an orchestra by only watching the conductor's hands, never hearing a single note of the music. We saw the afterglow of these mergers in the structure of galaxies, in the blaze of quasars. We saw the circumstantial evidence, the crime scene left behind, but we could never witness the act itself. We could never hear the scream, until now, because we have built a new kind of sense, a new way to perceive the universe that does not rely on light. We have constructed immense instruments, not to look at the sky, but to listen to it, to feel the infinitesimal tremors of a passing gravitational wave, the echo of a distant colliding universe. This is the dawn of a new astronomy, a new epoch of discovery, as revolutionary as when Galileo first pointed his telescope at the heavens. We are on a quest to hear these ancient sounds, to decipher their message, to finally witness the loudest events in history and understand the role they play in writing the grand cosmic story, a story that connects the chaotic birth of the first galaxies to the one we now call home. The central mystery is no longer if these events happen, but how. How do we find them? How do we interpret their gravitational song? And what will that song ultimately tell us about the universe and our place within it? The hunt is on. The silent symphony of space-time is playing all around us. We just need to learn how to listen. In the grand silent theatre of the cosmos, there are events so violent, so cataclysmic, they shake the very fabric of space-time itself. They are the loudest moments in the history of everything, yet they unfold in a vacuum so complete they make no sound at all. How do we listen to a silent scream that echoes across billions of years? The story begins not with a bang, but with a thought born in the mind of a single man grappling with the deepest nature of reality. In 1915, Albert Einstein gave us his general theory of relativity, a radical new vision of the universe. It was not a stage on which objects moved, but a dynamic four-dimensional entity called space-time, capable of being warped, bent, and curved by mass and energy. Planets were not pulled by an invisible force from the sun. They were following the straightest possible path through the curved space the sun had created. It was a masterpiece of human intellect, elegant and profound. But within the beautiful architecture of his equations, a monster was hiding. Just months after Einstein published his theory, a German physicist named Karl Schwarzschild, serving on the Russian front during the First World War, found the first exact solution to those complex equations. He was calculating the gravitational field of a single non-rotating star, a seemingly straightforward problem, yet his solution contained a terrifying prophecy. It showed that if you could squeeze enough matter into a small enough space, a point would be reached where the curvature of space-time becomes infinite. The escape velocity would exceed the speed of light. At this boundary, what we now call the event horizon, space-time collapses so completely that it effectively tears a hole in the universe. It becomes a one-way door. Nothing that crosses it, not a planet, not a star, not even light itself, can ever get back out. At the center of this gravitational abyss lay the singularity, a point of infinite density where all the known laws of physics break down. Einstein was horrified. He believed these Schwarzschild singularities were a mathematical monstrosity, a blemish on the face of his beautiful theory. He was convinced that in the real universe some unknown physical principle must intervene to prevent their formation. For decades, this remained the consensus. These objects, later nicknamed black holes, were relegated to the fringe, a mathematical curiosity too strange to be real. They were called frozen stars, objects whose light was so stretched by gravity that time itself would appear to stop at their surface for a distant observer. They were ghosts in the machine of relativity, and for half a century the vast majority of scientists were content to leave them buried in the mathematics. But the universe, it turns out, is stranger than even Einstein imagined. The first hints of the monster's true nature came not from theorists, but from a new breed of astronomer pioneers pointing strange new instruments at the sky. By the 1950 seconds, we had learned to see the cosmos in a new light, not just the visible light our eyes are tuned to, but the invisible spectrum of radio waves. This new field of radio astronomy revealed a universe buzzing with energy, filled with objects that were faint or completely invisible to optical telescopes. Among the most perplexing of these were a series of incredibly bright point-like radio sources. They looked like stars, so they were given a placeholder name, quasi-stellar radio sources, or quasars for short. But they were a profound cosmic riddle. When astronomers tried to analyze their light, their spectra, it was a meaningless jumble of lines that corresponded to no known element. They were celestial misfits broadcasting with immense power, yet speaking a language we simply could not understand. The breakthrough came in 1963 at the Palomar Observatory in California. An astronomer named Martin Schmidt was studying the spectrum of 3C 273, one of the brightest quasars in the sky. He stared at its bizarre pattern of emission lines for months, growing ever more frustrated. Then, in a moment of sheer scientific epiphany, he had a radical thought. What if the pattern wasn't from a strange new element at all? What if it was the most common element in the universe, hydrogen, but its spectral signature was distorted beyond all recognition? He realized the lines were in the right pattern, but shifted, massively shifted towards the red end of the spectrum. This redshift is the universe's own speedometer. It's the stretching of light waves caused by the expansion of space itself, telling us how fast an object is receding from us, and therefore how far away it is. When Schmidt calculated the redshift for 3C 273, the result was staggering. This tiny point of light was not a star in our own galaxy. It was located nearly 2.5 billion light-years away. The implications were almost too fantastic to believe. To appear as bright as it did from such an immense distance, 3C 273 had to be generating a colossal amount of energy. It was blazing with the light of more than 2 trillion suns, outshining our entire Milky Way galaxy by a factor of 100. And subsequent observations revealed another even more baffling fact. This incredible output of energy flickered its brightness, varying over months, which meant the source of this power had to be incomprehensibly compact, no larger than our solar system. You were being asked to accept an object smaller than a solar system that was outshining an entire galaxy containing hundreds of billions of stars. It was a violation of cosmic common sense. What kind of engine could possibly drive such a celestial blowtorch? The puzzle of the quasars forced scientists to confront the ghost that had been haunting physics for 50 years. In the mid-1960 seconds, a few bold theorists, like Donald Lynden Bell and Martin Rees in the United Kingdom and Yakov Zeldovich in the Soviet Union, proposed an answer that was as terrifying as it was elegant. The engine at the heart of a quasar, they argued, was one of Einstein's monsters now grown to an unimaginable scale. It was a supermassive black hole, not the remnant of a single dead star, but a behemoth weighing millions or even billions of times the mass of our Sunday. This gravitational titan would sit at the center of a young galaxy, a cosmic drain in the heart of a city of stars. Gas, dust, and even entire stars drawn in by its relentless gravity would not fall straight in. Instead, they would be whipped into a furious, flattened, spinning vortex called an accretion disk. As this maelstrom of matter swirled closer and closer to the event horizon, friction and magnetic forces would heat it to millions of degrees, turning it into an incandescent plasma, the brightest thing in the universe. This accretion disk was the true source of the quasar's light. The black hole itself remained unseen, a dark heart powering a brilliant shroud. The quasar was not the monster itself, but the monster's roar. It was the light of matter's final violent moments before being swallowed by infinity. This theory explained everything: the immense power, the compact size. It transformed black holes from a mathematical absurdity into a central component of cosmic evolution. They were the engines of creation and destruction, the power behind the most luminous objects we had ever witnessed. But this all took place in the distant ancient universe. Quasars were beacons from a cosmic dawn that had long since faded. The galaxies around us today are far more placid. Did that mean these monsters had died out? Or were they still here, lurking silently in the dark, their brilliant accretion disks, long since starved of fuel? If this theory was correct, then one of these titans should be hiding in the one place we knew best, our own cosmic home, the Milky Way. The hunt was on for the monster in our own backyard. The center of our Milky Way galaxy in the direction of the constellation Sagittarius is a place of extraordinary chaos and beauty, but it is also shrouded in secrecy. Vast, impenetrable clouds of interstellar dust and gas block our view in visible light, creating a cosmic curtain between us and the galactic core. For centuries, the heart of our own galaxy was a mystery, but where light fails, other messengers can succeed. Radio astronomers had long ago identified a powerful and compact radio source at the precise dynamical center of the galaxy. They called it Sagittarius A star, or Scurae asterisk. It was intriguing, suspicious, but it was not definitive proof. To find the monster, we needed to see the stars moving around it. We needed to catch it red-handed by its gravity. This would require a technological leap, a way to pierce the dusty veil and see the galactic center with a sharpness never before achieved. The key was infrared light, which can penetrate the dust, combined with a revolutionary technique called adaptive optics. This technology allows ground-based telescopes to correct for the blurring effect of Earth's atmosphere, in real time producing images as sharp as if they were taken from space. Two teams of astronomers on opposite sides of the world embarked on what would become one of the most patient and epic vigils in the history of science. One team was led by Reinhard Genzel at the European Southern Observatory in Chile. The other was led by Andrea Ghez at the Keck Observatory in Hawaii. For more than 2 decades, night after night, year after year, they pointed their powerful telescopes at the galactic heart. They weren't looking for the black hole itself. That would be impossible as it emits no light. They were tracking the stars closest to it, a small cluster of bright suns caught in its gravitational grip. They were watching a silent celestial dance, and slowly, painstakingly, the story began to emerge, plotted out point by point on a graph. The stars were not moving randomly, they were executing precise high-speed orbits. One star in particular, named S2, became the golden key. Ghez and Genzel's teams tracked its complete journey, a 16-year waltz around an unseen partner. They watched as it whipped around its closest approach, traveling at over 7,000 kilometers per second, nearly 3% of the speed of light. The movements of these stars were a gravitational fingerprint, using the simple, elegant laws of orbital mechanics first laid down by Johannes Kepler. The astronomers could calculate the exact mass of the object these stars were being forced to orbit. The answer was unambiguous and stunning. At the center of the Milky Way, confined to a space smaller than our inner solar system, was a single dark object with a mass of 4 million suns. It was too massive, too dense, and too dark to be anything else. It could not be a star cluster, as the stars would have collided and dispersed long ago. It had to be a supermassive black hole. After decades of being a theoretical ghost, a controversial engine for distant quasars, the monster was finally proven to be real. And there was one right here at home. This Nobel Prize-winning discovery was a watershed moment. It confirmed that supermassive black holes were not just relics of a violent cosmic past, they are a fundamental part of a galaxy's present-day anatomy. And when we turned our most powerful observatories like the Hubble Space Telescope to other galaxies, we found the same story repeated again and again. We saw the gravitational signatures of stars orbiting unseen centers. We saw the shadows cast by their event horizons. We realized that virtually every large galaxy, from our nearest neighbors to the most distant ones we can see, harbors one of these gravitational anchors in its core. They are not aberrations, they are the rule. These silent sleeping giants are the gravitational heartbeats of their galaxies, dictating the motions of stars, shaping their evolution, and holding everything together in a delicate cosmic balance. But galaxies are not solitary islands. They drift through the cosmos, pulled by gravity into great clusters and filaments, and over the vast timescales of cosmic history, they inevitably collide. We can see these majestic collisions happening all across the universe, great tidal streams of stars being ripped apart and reformed in a celestial dance that lasts for hundreds of millions of years, which leads us to a new and truly profound question. We have established that galaxies collide. We have established that every large galaxy has a supermassive black hole at its center. So what happens to those central black holes when their host galaxies begin this violent final embrace? What happens when two objects, each millions of times the mass of the Sun, each a rip in the fabric of reality itself, are set on an inescapable collision course? The universe prepares itself for a confrontation of titans, an event that will not be seen in light, but will be felt as a tremor in the structure of space-time. A storm of gravity is coming, and it will be the loudest thing the universe has ever known. But a theory, no matter how elegant, remains a ghost in the machine without the hard currency of observation. If our cosmic story is true, if galaxies are built upon the bones of their devoured ancestors, then the universe must be littered with the evidence. And when we turn our great eyes to the sky, we find we are not looking at a crime scene. We are living in the middle of a city of beautiful slow-motion collisions. Look here at the antennae galaxies, a cosmic smash-up caught in the act. Two great spirals, once serene and majestic in their solitude, have spent the last few 100 million years locked in a gravitational cage match. They are a portrait of chaos rendered in starlight. You can see the wreckage, the ghostly veils of stars flung far into the intergalactic void. These are the tidal tails, magnificent streamers of suns and gas pulled from their parent galaxies, like strands of silk from a tapestry. They trace the terrible, graceful arcs of gravity's influence, a visual record of a force that can unmake a stellar metropolis. Within the mangled heart of the collision, something extraordinary is happening. The shockwaves from this cosmic impact have compressed vast clouds of hydrogen gas, igniting a firestorm of creation. Millions of brilliant blue-white stars are being born at a furious rate, a stellar baby boom fueled by galactic destruction. Each point of light in these glowing knots is a young, massive star burning through its fuel so intensely it will live for only a fraction of the time of our own Sunday. It is a profound paradox of the universe. From the most violent encounters comes the most fervent creation. And this is not an isolated incident, a singular spectacle. Our telescopes reveal a universe embroiled in this process of merger and acquisition. We see the mice galaxies, two spirals stretching toward each other, with long, thin tails like apparitions fleeing a gravitational haunting. We see Stephan's quintet, a tightly knit gang of galaxies tangled in a complex dance, their structures warped and distorted by repeated close passages. These are not static pictures. They are snapshots of a process that unfolds over eons. For us, it is a silent film, but for the universe, it is a fundamental part of its own evolution. Everywhere we look, we see the proof that galaxies do collide, that they do merge, and that the universe is constantly rebuilding itself from its own rubble. These images, as breathtaking as they are, only show us the grand stage. They are the wide shot of the drama. But our central mystery lies hidden deep within the chaos at the very heart of these colliding worlds. For if each of these merging galaxies hosted its own supermassive black hole, a dark monarch at its core, then gravity dictates an unavoidable fate. As the galaxies intertwine, their central monsters, once separated by millions of light years, begin a long, inexorable journey toward one another. The dance of the galaxies becomes the prelude to a far more intimate and violent duet, the death spiral of two singularities. Finding these merging behemoths, however, is a challenge of cosmic proportions. They are hidden from our view, shrouded by the dust and gas and the blinding light of billions of stars in the newly formed galactic core. Looking for two supermassive black holes is like trying to spot two moths circling a searchlight during a hurricane from a continent away. Our conventional telescopes, which see the universe in forms of light, are almost entirely blind to them. So astronomers had to become detectives, looking not for the culprits themselves, but for the disturbances they create in their environment. The first major clue comes from a phenomenon we had already witnessed across the cosmos, the incandescent fury of an active galactic nucleus, or AGN. As we've seen, when a supermassive black hole is actively feeding, it can become the most luminous object in the universe. The maelstrom of matter swirling into its maw heats up to unimaginable temperatures, blasting out radiation across the entire electromagnetic spectrum. It becomes a celestial blowtorch, a quasar outshining all the billions of stars in its own galaxy combined. Now consider what happens when a galaxy merger occurs. The collision funnels colossal amounts of gas and dust toward the galactic center, providing a sudden, extravagant feast for the resident black hole. A dormant giant awakens, and the galaxy's core lights up like a beacon. This gave astronomers a brilliant, if indirect, strategy. If a galaxy merger provides the fuel to ignite one black hole into an AGN, then a merger involving two supermassive black holes should, in theory, ignite both times of them. The mission then was to hunt for a very specific signature, a single disturbed-looking galaxy that appeared to have two brilliant active hearts. A system known as a dual-active galactic nucleus. Finding one would be like finding two separate lighthouses spinning wildly inside the same churning foggy bay. It would be the first concrete proof that two supermassive black holes were on a collision course. The search began sweeping the skies for these rare and elusive pairs. Astronomers sifted through mountains of data from radio telescopes, X-ray observatories, and optical surveys looking for the telltale signs. Sometimes they would find a galaxy with a core that was strangely elongated, as if two distinct points of light were blurred into one. Other times they would analyze the spectrum of light coming from a quasar and find evidence of two different velocity systems, as if two separate accretion disks were spinning at different speeds, orbiting each other in the same gravitational field. For decades, the evidence was tantalizing but maddeningly ambiguous. Candidate after candidate was proposed, studied, and often dismissed. The distances are just too vast, the objects too close together to be cleanly resolved. But then came discoveries that seemed to solidify the case. Consider the galaxy NGC 6240, a chaotic, butterfly-shaped wreck of a galaxy, clearly the product of a recent merger. Peering deep into its core with the Chandra X-ray Observatory, astronomers found not one but two intensely bright sources of X-rays. Two distinct superheated cores separated by just 3,000 light-years. Two voracious monsters circling each other, each powering its own AGN. And then there is the even more extraordinary case of a quasar known only by its catalogue number SDSSJ 1010 plus 1413. Looking at its light signature, scientists noticed a peculiar rhythmic wobble, a subtle repeating shift in its spectral lines, like a siren whose pitch rises and falls as it rushes past. The best explanation was a breathtaking one. We were not seeing a single object but two quasars locked in a tight orbit, a binary system of feeding supermassive black holes. One moving towards us in its orbit had its light blue shifted. The other, moving away, was red-shifted. The pair were separated by less than a single light-year, whirling around each other in a celestial waltz that took only a few years to complete. We had found them. Not just in the same galaxy, but in the same gravitational embrace. These discoveries were monumental triumphs. They provided the first direct electromagnetic evidence that supermassive black holes not only coexist in merging galaxies, but are drawn together by gravity, destined to orbit as binary pairs. The theory was becoming reality. The grand cosmic narrative from colliding galaxies to orbiting behemoths seemed complete. The stage was set for the final cataclysmic act of merger. And it is here, on the very brink of discovery, that we slammed headfirst into one of the most stubborn and perplexing paradoxes in modern astrophysics. A theoretical brick wall known with unnerving simplicity as the final parsec problem. The physics of the merger seems straightforward at first. Imagine our two supermassive black holes now captured in a mutual orbit within the dense, star-filled core of their newly merged galaxy. Initially, they are separated by thousands of light-years, but they have a powerful mechanism for shedding their orbital energy and drawing closer. This mechanism is called dynamical friction. It is, in essence, a gravitational wake. As each massive black hole plows through the sea of surrounding stars, its immense gravity pulls those stars toward it. The stars are dragged along for a short while, forming a dense cluster, a wake behind the black hole. The collective gravity of this stellar wake then pulls back on the black hole itself, acting like a cosmic parachute, slowing it down. As both black holes slow, they cannot maintain their wide orbit. They sink inevitably toward the center. For millions of years, this process is brutally efficient. The two giants act like gravitational bullies, kicking countless smaller stars out of the central region in a series of three-body interactions. Each star they eject carries away a tiny parcel of the binary's orbital energy. With each ejection, the black holes pay a price, their orbit tightening, their spiral quickening. They shrink their orbit from thousands of light-years down to a few hundred, then down to tens of light-years. They have cleared a path, creating a barren zone around them, a celestial arena emptied of its spectators. And then, when they are separated by a distance of about 1 parsec, roughly 3¼ light-years, the process grinds to a halt. Suddenly, the dynamical friction fails them. They have become too efficient for their own good. They have ejected all the nearby stars that were easy to interact with. The stellar sea through which they once swam has been drained. There is nothing left nearby to create a gravitational wake, nothing to act as a parachute, no more small objects to fling away to bleed off energy. The two supermassive black holes are now trapped. They are locked in a stable binary orbit circling one another for eternity. They can get no closer. According to the simplest models of this interaction, their death spiral just stops. They are doomed to waltz forever in this final parsec, a cosmic standoff that could last for billions upon billions of years, longer than the current age of the universe. This is the final parsec problem, and it presents a profound cosmic contradiction. Our observations of the universe tell us that large galaxies are the product of countless mergers. This implies that supermassive black holes must merge and merge, often to account for the colossal giants we see today. Yet our understanding of physics, of gravity and dynamics presents us with this infuriating impasse, this waiting room from which there is no escape. It's as if we have a detailed account of 1,000 criminals leaving their homes and 1,000 victims at the morgue, but the security footage cuts out just as the killer is about to enter the room. The beginning is clear, the end result is known, but the crucial final act is a complete physical mystery. How does nature solve this puzzle? How does it bridge this final unbridgeable gap? For years, theorists have wrestled with this question, proposing a host of potential solutions. Perhaps the answer lies not in stars, but in gas. If the merging galaxies were rich in gas, that material would also fall to the center, forming a vast circumbinary disk around the orbiting black holes. The black holes moving through this dense medium would experience a form of drag, like two anchors being pulled through thick mud. This friction could be enough to sap the last dregs of their orbital energy, allowing them to finally spiral inward and touch. This is a promising idea, but it requires a very specific set of circumstances, a galaxy with an enormous reservoir of cold gas delivered precisely to its core. It might work sometimes, but can it be the universal solution? Another possibility is more chaotic. The universe is rarely a simple two-body problem. What if a third supermassive black hole from another later galaxy merger were to wander into this stalled binary system? The resulting three-body interaction would be gravitationally unstable. Typically, such an encounter ends with the lightest of the three bodies being ejected at tremendous speed, a cosmic slingshot effect. The remaining two, having given up their energy to the ejected member, would recoil into a much tighter orbit, possibly tight enough to finally merge. But this too feels like a special case, a cosmic coincidence, rather than a reliable mechanism. It cannot be the routine process that allows black holes to grow in lockstep with their galaxies, so we find ourselves at a precipice of understanding. We have followed the evidence from the grand galactic scale down to the intimate dance of two ravenous giants. We have used our telescopes, our instruments of light, to trace their journey from across the cosmos to the doorstep of their final union. And there, in that last crucial parsec, our vision fails us. Light, the messenger that has taught us almost everything we know about the universe, can no longer show us the way forward. The electromagnetic clues run dry, leaving us staring into a theoretical void. The two most massive objects in the universe are trapped, circling each other in a silent, unending standoff, and we are left with no way to see how their story ends. It is a problem that seems to demand a new kind of observation, a new sense. If we can no longer times the final moments of this cosmic merger, perhaps, just perhaps, there is a way for us to times listen, to listen for the sound that would be made not by matter, but by the very fabric of space-time itself, as it is twisted and torn and finally broken by the collision of two titans. We need to search for a whisper that has been traveling across the cosmos for billions of years, carrying the secret of the final parsec with it. We need to search for the sound of gravity itself. For generations, the final parsec remained an impenetrable wall. It was a zone of silence in our cosmic story, a chapter torn from the book of galactic evolution just before the climax. We had followed the grand waltz of galaxies, we had watched them draw closer in a gravitational embrace, and we had traced the spiraling paths of their central supermassive black holes, destined for a union of unimaginable power. Yet in that final, crucial light year, the trail went cold. Our telescopes, our most powerful eyes on the universe, were blind to the intimate details of this ultimate dance. Our computers, struggling with the ferocious physics, ground to a halt. We knew the crescendo had to happen, but we could neither see it nor hear it. The universe, it seemed, was keeping its greatest secret. The answer, when it finally began to dawn, would not come from looking harder at the distant cores of galaxies. It arrived from an entirely different direction, born from a century-old prediction and an instrument of such audacious sensitivity it bordered on the impossible. It came not as light but as a vibration, a tremor in the very fabric of reality. To understand this monumental shift, you must first reimagine your universe. We are accustomed to thinking of space as an empty stage, a black passive void across which stars and planets move. But Albert Einstein, in his profound insight of general relativity, revealed a completely different reality. He showed us that space and time are not separate, nor are they a static backdrop. They are woven together into a single dynamic entity, a four-dimensional fabric called space-time. It is this fabric that dictates the motion of everything. A planet does not orbit a star because of a mysterious invisible rope pulling on it. Instead, the immense mass of the star creates a deep depression, a gravitational well in the space-time fabric around it. The planet, attempting to travel in a straight line, simply follows the curve of this well like a marble rolling around the edge of a vast invisible funnel. This is gravity, not a force but the geometry of the cosmos itself. And like any fabric, space-time can be disturbed. It can ripple, it can quiver, it can carry waves. If you toss a stone into a perfectly still pond, you see ripples spread outward, carrying energy from the splash. Einstein predicted that the universe works in a similar way. Any time a massive object accelerates, when it changes its speed or direction, it should send ripples propagating outward through the fabric of space-time. These are not waves traveling times through time-space like light or sound. They are waves times of time-space itself. As a gravitational wave passes by, it literally stretches and squeezes the space it moves through. The distance between 2 points will momentarily lengthen in one direction, while simultaneously shortening in the perpendicular direction. The effect is impossibly subtle. A passing gravitational wave would stretch a human being from head to toe by a distance less than the width of a single atomic nucleus. And it would do so without you feeling a thing, because every atom in your body and all the space between them would be stretched and squeezed in perfect concert. To all of our biological senses, these cosmic tremors are utterly imperceptible. They are the silent song of gravity, a ghostly messenger from the most violent events in the universe, passing through us, through the Earth, through entire galaxies, as if they were nothing. For nearly a century, this idea remained one of the most exotic and unproven predictions in all of physics. How could you possibly build a machine sensitive enough to measure a distortion in space so infinitesimally small? The challenge was beyond daunting. It was for many considered a fool's errand, yet a small group of visionary scientists refused to let the dream die. They imagined an instrument, a gravitational wave observatory that would function not like a telescope but like a colossal celestial ear, an instrument that would listen for the faint ringing of the space-time bell. Their vision, realized after decades of tireless effort and brilliant innovation, was the Laser Interferometer Gravitational Wave Observatory, or LIGO. The name belies the sheer scale and elegance of its design. It is one of the most magnificent scientific instruments ever conceived by humankind, a testament to our relentless curiosity. Picture two massive arms, each stretching 4 kilometers long, arranged in the shape of an L. They are housed within perfectly straight vacuum tubes sealed off from the disruptive noise of our world. Inside, the air has been pumped out to a pressure 1/1,000,000,000th that of our atmosphere, creating one of the most pristine vacuums on Earth. At the corner of this L, a powerful laser is split into two identical beams. One beam is sent racing down one arm, the other down the second. At the far end of each arm hangs a mirror, a near perfectly polished silica disc suspended by delicate glass fibers to isolate it from the slightest terrestrial vibration. These mirrors are so smooth that if you were to scale one up to the size of a continent, the largest imperfection would be no bigger than a grain of sand. The two laser beams strike these mirrors and reflect back to the corner where they started. There they are recombined. The entire system is an exquisitely precise ruler for measuring space-time itself. If the two arms are of an absolutely identical length, the two returning light waves should meet and, through a property called interference, completely cancel each other out. No light would reach the detector. But if a gravitational wave were to sweep across the Earth, its effect would be subtle but profound. As it passed, it would momentarily stretch one of LIGO's arms while simultaneously squeezing the other. Suddenly, the two paths traveled by the laser beams would no longer be identical. One beam would have to travel a fractionally longer distance, the other a fractionally shorter one. When they recombined at the corner, they would no longer be perfectly out of sync. They would fail to cancel each other out, and a flicker of light, a tiny signal, would strike the detector. That flicker is the gravitational wave. That flicker is the sound of the universe speaking. The engineering required to achieve this level of sensitivity is almost beyond comprehension. LIGO must be able to detect a change in the length of its 4-kilometer arms of 1/10,000th the diameter of a proton. This is equivalent to measuring the distance to the nearest star, Proxima Centauri, with an accuracy smaller than the width of a single human hair. The project is an unending war against noise. Every possible source of disturbance, from a passing truck on a distant highway to the gentle lapping of ocean waves on a coastline hundreds of miles away, to the quantum jitter of the laser light itself, had to be anticipated, measured, meticulously cancelled out. Seismic isolation systems involving layers of active and passive dampers were built to act as a colossal shock absorber, rendering the multi-ton mirrors practically motionless, floating free in space. For years, the detectors listened, hearing only the cacophony of Earth and the instrument's own internal rumblings. The silence from the cosmos was deafening. The scientists refined, they upgraded, they pushed the technology to its absolute limits, waiting with a patience bordering on faith. Then, on September 14th, 2015, at 9, 5, 0, and 45 seconds, Coordinated Universal Time, the universe broke its silence. A vibration, clear and unambiguous, swept through the planet. It was detected first at the LIGO Livingston Observatory in Louisiana. Just 7 milliseconds later, having travelled at the speed of light, the same wavefront washed over the LIGO Hanford Observatory in Washington State, 3,000 kilometers away. It was not a glitch. It was not a truck. It was not an earthquake. It was real. When the data was converted into an audible sound wave, it produced a faint, rising chirp, a sound that lasted for less than a quarter of a second. It was the whisper they had spent half a century preparing to hear. That tiny, fleeting sound was the death cry of two black holes. Analysis of the signal painted a breathtaking picture of a cataclysm that had occurred 3 billion years ago in a galaxy so distant that when the event took place, the most complex life on Earth was simple multicellular algae. Two black holes, one about 29 times the mass of our Sun, the other around 36 times, had been locked in a death spiral for eons. In the final moments of their existence, they were whipping around each other hundreds of times per second, moving at more than half the speed of light. As they drew closer, the space-time around them was being churned into a maelstrom, shedding gravitational waves of ever-increasing frequency and intensity, creating that telltale cosmic chirp. And then they merged. In a fraction of a second, the two black holes fused into one, forming a new single black hole of about 62 solar masses. But if you do the math, something seems wrong. 29 plus 36 is 65, not 62. Where did the missing 3 solar masses go? In that final, violent moment of coalescence, the mass of 3 entire suns was converted in an instant into pure gravitational energy, radiating away into space in the form of gravitational waves. For that briefest of moments, the power of this single merger outshone the combined light of every star in every galaxy in the observable universe. It was quite simply the most energetic event human beings had ever directly detected since the Big Bang itself. And we felt it. Across 1.3 billion light-years of expanding space, that titanic shudder propagated, weakening with distance, until its final ethereal tremor passed through the Earth, gently nudging LIGO's mirrors by an infinitesimal amount and announcing its arrival. It was the dawn of a new era. We had been deaf to the universe, and suddenly we could hear. This first detection, designated GW150914, was more than just a discovery. It was a profound paradigm shift. For all of human history, our knowledge of the cosmos had come from light. From visible light to radio waves, from X-rays to gamma rays, we had relied on the electromagnetic spectrum to paint our picture of reality. But this was something entirely new. It was a new sense. It was as if a species that had only ever known sight was suddenly granted the ability to hear. We were now able to perceive the universe not just through its light, but through its vibrations, through the very warping of its structure. This was gravitational wave astronomy, and it gave us access to the truly dark side of the universe, to phenomena like black holes which by their very nature emit no light, and had previously only been inferred by their effects on the objects around them. Now we could listen to them directly. We could hear them collide. The success of LIGO sent shockwaves through the entire astronomical community. While the teams celebrated their monumental achievement, the direct observation of stellar mass black holes, a Nobel Prize-winning feat in its own right, another group of scientists saw something more. They saw a key, a Rosetta Stone that could finally unlock the mystery that had plagued them for so long, the final parsec problem. The logic was powerful and inescapable. If the merger of 2 black holes each just a few dozen times, the mass of our sun could produce a signal strong enough to be detected from over 1 billion light-years away. What kind of signal would be produced by the titans at the heart of galaxies? What cosmic symphony would be played by the place? The merger of 2 black holes, not 30 but 30 times billion times the mass of our sun. The answer was breathtaking. The physics predicted that the gravitational waves from such a colossal event would be of a fundamentally different character. The final frantic chirp of stellar mass black holes happens at frequencies of a few hundred hertz, well within the range of human hearing. If they were sound waves, we could listen to their final moments. But supermassive black holes are vastly larger and more ponderous. Their orbital dance is a slow, majestic affair, taking years, even decades, to complete their final spirals. The gravitational waves they produce would therefore have extraordinarily long wavelengths and incredibly low frequencies. They would not create a brief, high-pitched chirp. Instead, they would generate a deep, persistent, ultra-low frequency drone, a signal with a frequency measured in nanohertz, a billionth of a cycle per second. One single wave could take 30 years to pass you by. This is not the sound of a single, isolated event. Because we believe these supermassive mergers are happening all across the universe throughout cosmic time, the signals from all of them should be arriving at Earth simultaneously. They would overlap, interfering with each other to create a continuous stochastic background. It would not be a solo performance, but the sound of an entire cosmic orchestra, a relentless, ever-present gravitational wave hum underpinning the entire universe. This is the sound we had been missing. This is the evidence that had eluded our telescopes. The final parsec problem was not a wall of silence because nothing was happening. It was a wall of silence because we had been trying to see an event that could only be times heard asterisk. We had been searching for a flash of light, in a realm governed by a deep resonant vibration. The detection of GW 150914 had, in a flash of insight, redefined the entire quest. The challenge was no longer to peer through the gas and dust of a galactic core, hoping to glimpse the final moments of a merger. The new challenge was to learn how to listen for this cosmic bass note. The monumental success of LIGO proved that gravitational waves were real and detectable, but its design made it fundamentally deaf to the ultra-low frequencies of the supermassive giants. Its 4-kilometer arms are far too short to register a wave that is light-years long. To hear this primordial hum, we would need a detector of a completely different kind. We would need a detector not kilometers, but thousands of light-years across. We would need to build an observatory on a galactic scale, and remarkably the universe had already built one for us. We just had to learn how to use it. That triumphant chirp, the sound that echoed from LIGO's detectors and shook the foundations of astrophysics, was the sound of a new sense being born. For the first time we could hear the universe. We had captured the violent, fleeting scream of two stellar mass black holes, each just a few dozen times the mass of our Sun, as they spiraled into a final explosive embrace. It was a revolution, a testament to human ingenuity, and yet in the afterglow of that spectacular success, a profound and unsettling silence remained. We had tuned our cosmic ear to the piercing soprano of the cosmos, but the universe we knew also possessed a voice of unimaginable depth, a voice so low, so resonant that our magnificent laser interferometers were utterly deaf to it. The supermassive black holes, the galactic titans we had been hunting for decades, were still moving in complete and total silence. Their mergers, the cataclysms that reshape galaxies, do not sing in the kilohertz range that LIGO is built to detect. Their orbital dance is a far slower, more ponderous affair, a waltz of celestial dreadnoughts unfolding over millions of years. The gravitational waves they produce are not short, sharp chirps, but vast continent-sized swells in the fabric of spacetime itself. Their frequency is measured not in thousands of cycles per second, but in nanohertz billionths of a cycle per second. A single wave from crest to crest could stretch for light years. To detect such a colossal undulation, you would need a detector of commensurate scale, an instrument built not of mirrors and vacuum tubes, but of something far grander. You would need a detector the size of the galaxy itself. The very idea seems like a fantasy, a piece of science fiction. How could humanity confined to this one small planet possibly build such a thing? The answer, born from a stroke of staggering genius, was that we wouldn't have to build it at all. The universe, in its boundless generosity, had already built it for us. We just needed to learn how to listen with it. The key to this galactic-scale observatory was hidden within some of the most bizarre and extreme objects known to science. To find them, you must look toward the graveyards of giant stars. When a star far more massive than our Sun exhausts its fuel, it collapses under its own immense gravity and explodes in a supernova, a final incandescent roar that can briefly outshine its entire galaxy. What is left behind is a core so compressed that the very structure of matter is broken. Protons and electrons are crushed together to form a city-sized sphere made of pure neutrons, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. This is a neutron star. And sometimes, if the conditions are just right, this stellar remnant is born, spinning with a furious hypnotic regularity, sweeping beams of intense radiation out from its magnetic poles. As it spins, these beams of energy flash across our line of sight, again and again and again, like the ceaseless rhythmic pulse of a celestial lighthouse. We had discovered a pulsar. First detected in 1967 by a young graduate student named Jocelyn Bell Burnell, these objects were initially so precise they were playfully labelled LGM, one for little green men, as no known natural phenomenon was thought to be, capable of such astonishing clockwork. The mystery was soon solved, but the miracle of their timing remained. They are nature's most perfect clocks, cosmic metronomes set ticking by the laws of physics at their most extreme. Their rotation is governed by the conservation of angular momentum, a principle so fundamental that their stability rivals, and in some cases exceeds that of our best atomic clocks on Earth. They are gravitational gyroscopes, their spin a near-perfect constant, a rhythmic beat against which we could measure the cosmos. But even among these marvels of stability, there exists an elite class, the millisecond pulsars. These are older pulsars, often found in binary systems, with a companion star that have been spun up by accreting matter from their partner, like a child's top being whipped into a frenzy. They rotate not just once or twice a second, but hundreds of times, their pulses arriving with a precision that is nothing short of breathtaking. Here then were the components of our galactic detector. These millisecond pulsars scattered across the Milky Way like glowing pins on a vast dark map were our instruments. The audacious idea was to not just listen to one, but to monitor dozens of them simultaneously, creating a network, a web of precisely timed signals crisscrossing thousands of light years of space. This grand project became known as a pulsar timing array, or PTA. Collaborations like Nanograv in North America, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array in Australia began a patient, meticulous vigil. For years then, decades, radio telescopes around the world would stare at these specific points of light, catching the faint whisper-thin radio pulses that had travelled for millennia to reach us. They were logging the exact arrival time of each and every pulse down to the nanosecond building, a library of cosmic timekeeping on an unprecedented scale. It was a slow, painstaking process, an astronomical marathon requiring immense dedication and a deep faith in the theory. The principle behind it is as elegant as it is ambitious. Imagine you are standing in the middle of a perfectly still lake, and all around you at various distances are buoys that send out a perfectly regular ping every single second. You record the arrival time of every ping from every buoy. Now imagine a massive invisible submarine glides silently through the deep water. As it moves, it creates a long, slow, powerful swell on the surface. That swell would travel outwards, and as it passed each buoy it would gently lift it up and then set it back down. For the buoy, this means its distance from you has changed first, becoming slightly shorter, then slightly longer. The pings you receive from that buoy would therefore arrive a tiny fraction of a second early, and then a tiny fraction of a second late. If you only watched one buoy, you might dismiss this tiny anomaly as noise, a random glitch. But if you are watching dozens of buoys, you would see a correlated pattern emerge. Buoys in one direction would see their pings arrive early, while buoys in another direction would see their pings arrive late, all in a coordinated, slowly shifting pattern that traces the passage of the invisible swell. This is precisely how a pulsar timing array works. The pulsars are the buoys. The radio pulses they emit are the pings. Our radio telescopes on Earth are the observer in the center of the lake. And the vast, slow swell passing through the cosmic ocean is a gravitational wave from a merging pair of supermassive black holes. As this colossal wave of warped space-time washes through our sector of the galaxy, it gently stretches and squeezes the very fabric of reality. It subtly alters the distance between Earth and each pulsar in the array. When the space between us and a pulsar is compressed, its radio pulses will arrive a few nanoseconds ahead of schedule. When the space is stretched, they will arrive a few nanoseconds behind. A nanosecond, a billionth of a second, is the time it takes light to travel just 1 foot. We are searching for a timing deviation equivalent to the length of your shoe across a distance of thousands of light years. It is a measurement of almost hallucinatory precision, a search for a whisper in a hurricane of galactic noise. The challenge is monumental. The signals from these pulsars are incredibly faint, and on their long journey to Earth they are jostled and delayed by all manner of interstellar interference. Clouds of free electrons in the interstellar medium can scatter the radio waves, smearing out the pulse and altering its arrival time. The inherent jitter of the pulsar itself, tiny instabilities in its rotation, can create noise that mimics the signal we're looking for. Even the precise motion of our own solar system, the wobble of the Earth on its axis, and its journey around the Sun must be modelled and subtracted with absolute perfection. The astronomers working on this problem are like cosmic detectives, meticulously accounting for and eliminating every possible source of contamination, every red herring that could lead them astray. They build complex models of the interstellar medium, refine our understanding of the solar system's gravitational dynamics, and create sophisticated algorithms to sift through mountains of data. Their vigil is a multi-generational quest. They are not looking for a single dramatic chirp like LIGO heard. At first, they are searching for something far more subtle, a persistent, low-level hum. The universe is filled with countless pairs of supermassive black holes, all slowly spiraling together in the hearts of distant galaxies. While each individual merger is a discrete event, their combined chorus creates a stochastic gravitational wave background, a ceaseless cosmic rumble like the murmur of a distant crowd. This is the first signal the PTAs expect to find. It wouldn't be a clear note, but a specific type of correlated noise across all the pulsars in the array, a signature pattern of deviation unique to a gravitational wave background. It's like standing by the ocean on a foggy day. You can't see the individual waves, but you can hear the constant deep roar of the surf. Finding this background hum would be the first proof of principle, the confirmation that our galactic scale detector was working, that the universe was indeed singing in this deep bass register. For over 2 decades, the data accumulated pulse by painstaking pulse. Year after year, astronomers refined their techniques, added more pulsars to the array, and extended their observational baselines. They were looking for a specific correlation signature, a pattern predicted by Einstein's theory that says pulsars separated by 90 degrees on the sky should show the strongest correlation, while those closer together, or on opposite sides of the sky, should show weaker or even anti-correlation. This unique spatial fingerprint, known as the Hellings and Downs curve, is the smoking gun. It's the one pattern that cannot be explained by instrument noise or solar system errors. It is the unambiguous signature of gravitational waves washing over our cosmic neighborhood. The search was a slow, arduous process of building up signal to noise. Each new observation was another drop of water in a bucket, slowly raising the level of evidence. The teams held their breath, analyzed their data, and waited. They were listening for the deepest, most profound symphony in the universe, a sound forged in the hearts of colliding galaxies, a sound that carries the story of cosmic evolution. This hunt represents a profound shift in our perspective. With LIGO, we built an instrument to probe the universe. With pulsar timing arrays, we have realized that the universe times the instrument. We are not merely observers of the cosmos. We have become participants in its grand orchestra, using its most exotic stars as our sensors, its interstellar distances as our lever arms. We are leveraging the entire Milky Way as a scientific apparatus to listen for the echoes of creation and destruction on the grandest possible scale. The patience required is almost inhuman, a scientific vigil that spans entire careers. Every data point is a small act of faith, a belief that buried within the noise, hidden in those nanosecond deviations, lies the confirmation we seek. After so many years of silence, of patient listening, of straining to hear the faintest sound above the static, a question hung in the air, growing more urgent with each passing year. Was the hum getting louder? Were the whispers of the cosmic titans, after all this time, finally beginning to resolve into a discernible, magnificent song? For a generation, it was a vigil of almost monastic patience. Across the globe, colossal radio dishes, modern cathedrals of science, swiveled in the silent dark, their gaze fixed upon celestial metronomes scattered across our galaxy. These were the millisecond pulsars, the collapsed hearts of long-dead stars spinning with a regularity so profound they challenged our very best atomic clocks. For decades, astronomers listened not for a message but for a timing. They logged each pulse, billions upon billions of them, building a dataset of almost unimaginable precision, a testament to long-term faith in a theoretical prediction. They were listening for a ghost in the machine, a whisper buried beneath a hurricane of noise. They were listening for the faint, lingering echo of the loudest events in history. The premise, as we have seen, was as elegant as it was audacious to transform a portion of the Milky Way into a single galaxy-sized gravitational wave detector. Each pulsar was a clock in a vast cosmic grid, If a gravitational wave, a ripple in the very fabric of space-time, were to wash through our corner of the universe, it would subtly squeeze and stretch the distance between Earth and these pulsars. The effect would be infinitesimal, a delay or an advance in a pulse's arrival time, measured in mere nanoseconds spread out over years. A single pulsar's deviation would mean nothing. It could be an intrinsic stellar wobble or a cloud of interstellar gas. But the true signal, the telltale sign of a gravitational wave background, would not be random. It would be correlated across the entire sky in a very specific predicted pattern. This pattern, the theoretical key to unlocking the entire endeavor, is known as the Hellings and Downs curve. Imagine yourself on a calm lake with a network of buoys floating around you. If a single distant boat creates a wave, it doesn't just lift and drop one buoy. It creates a pattern of movement across all of them, with the motion of any two buoys correlated based on their distance from each other and their orientation to the wave. The Hellings and Downs curve is the gravitational equivalent of this. It predicts the precise mathematical relationship you should see in the timing jitters between any two pulsars in your array, depending only on their angular separation in the sky. Finding this specific quadrupolar signature, this unique celestial fingerprint, would be the smoking gun. It would be irrefutable proof that the space-time between us and those pulsars was being rhythmically distorted by a sea of gravitational waves. But for year after year, the search yielded nothing but deeper complexity and a growing respect for the universe's ability to mask its secrets. The data was a torrent of noise. The astronomers of the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, along with their colleagues in the European Pulsar Timing Array and Australia's Parkes Pulsar Timing Array, had to become masters of cosmic forensics. They first had to account for the physics of the pulsars themselves. These are not perfect machines. They exhibit their own timing, eccentricities, a type of stellar noise that had to be modeled and subtracted with painstaking precision for every single star in their array. Then came the journey of the signal itself. For thousands of years, each radio pulse has traveled through the turbulent ionized gas of the interstellar medium. This plasma acts like a cosmic fog, smearing out the pulse and altering its arrival time in ways that change unpredictably. The teams had to develop sophisticated techniques using multi-frequency observations to measure this distortion and peel it away from the data layer by painstaking layer. And even then, the greatest source of noise was, in a sense, ourselves. Our solar system is not a fixed point. It is in constant motion, orbiting the center of the Milky Way. To detect a nanosecond shift in a pulsar's timing, you must first know the exact location of your telescope relative to the center of mass of the entire solar system, the barycenter, to a precision of just a few hundred feet. Any error in our planetary maps, any slight miscalculation of Jupiter's orbit or the pull of a distant asteroid would create a false signal, a phantom ghost that could mimic the very thing they were hunting for. For more than 15 years, the NanoGrav team meticulously built their dataset, adding more pulsars, refining their models, and pushing against the walls of noise. In 2020, a tremor of excitement ran through the community. They had found a signal, a common hum across all the pulsars, but it was not yet definitive. It was a tantalizing hint, a possible scent of the prey, but the crucial Hellings and Downs spatial correlation, the unique fingerprint that would distinguish the growl of supermassive black holes from some unknown cosmic noise, remained. Elusive, buried just beyond the edge of their sensitivity. It was a moment of profound tension. They had spent their careers on this quest, and now they stood at a precipice. Was the theory wrong? Were the mergers too rare, their signal too faint, or did they simply need to listen with even greater patience for just a little longer? The answer came from the power of collaboration. By combining their hard-won data with their European and Australian counterparts under the banner of the International Pulsar Timing Array, they synthesized a dataset of unprecedented scale and maturity. It was like connecting multiple smaller telescopes into one giant continent-spanning eye. They now had a combined quarter-century of observations of dozens of pulsars. They fed this immense ledger of cosmic timekeeping into supercomputers, unleashing sophisticated Bayesian algorithms, statistical tools designed to find the faintest of melodies hidden within a symphony of chaos. The software churned for weeks, sifting through every possibility, every potential source of noise, every permutation of the data, relentlessly hunting for that one specific predicted pattern. And then it emerged. Slowly, as the statistical significance grew with each computational cycle, the ghost began to take form. From the fog of uncorrelated noise, a definite shape resolved itself. When the scientists plotted the correlation between pulsar pairs against their separation on Vesky, they saw it. The points didn't form a random scatter. They began to trace a distinct undulating curve. A curve that rose and fell with the exact shape, the exact mathematical grace that David Hellings and George Downes had predicted on a chalkboard 4 decades earlier. It was there. The fingerprint was a perfect match. The whisper they had been straining to hear for a generation was finally unmistakably loud enough to be understood. On June 28, 2023 inches, a series of coordinated announcements that electrified the world of astronomy, the collaborations revealed their discovery. The press conferences were not filled with a single dramatic image, like the first photograph of a black hole's shadow. Instead, they were filled with graphs that to the scientists who had dedicated their lives to this pursuit were the most beautiful sights in the universe. The data points, each one representing years of patient observation and brilliant analysis, fell almost perfectly along the theoretical line. The evidence was robust, the signal was unambiguous. After decades of listening to the silence, humanity had finally heard the background hum of the cosmos. What is it then that we are hearing? It is not a set of discrete chirps like the high-frequency screams of stellar mass black holes detected by LIGO. Those are the piccolos and violins of the cosmic orchestra, sharp individual notes from fleeting events. What the pulsar timing arrays have detected is the bass section. It is a profound stochastic, ever-present rumble, the superposition of thousands, perhaps millions of overlapping gravitational waves from every direction in the sky. It is the collective blended roar of countless pairs of supermassive black holes monsters, weighing millions or even billions of suns, all spiraling toward their cataclysmic mergers throughout the universe and throughout cosmic time. Imagine for a moment that you could translate this nanohertz gravitational wave signal into sound. It would be a tone impossibly deep, its wavelength measured in light years, its frequency thousands of times lower than the deepest note on a church organ. It is a chord that has been playing since the first galaxies began to collide, a constant churning vibration woven into the very structure of reality. It is the sound of cosmic construction. It is the sound of galaxies growing, of structure forming, of the universe building itself one titanic merger at a time. In detecting this gravitational wave background, we have not merely observed an event, we have tuned into the persistent ambient soundtrack of the universe itself. We have learned to hear the rhythm of cosmic evolution. This discovery sends shockwaves through our understanding of the cosmos, solving old paradoxes while simultaneously opening thrilling new avenues of inquiry. For decades, our models of galaxy formation have been built on a foundation of hierarchical merging. We believed that large galaxies like our own Milky Way were built up over eons through the collision and cannibalization of smaller ones. If this were true, then the supermassive black holes at their centers must also eventually meet and merge. Yet we had no direct proof. This constant universe-filling hum is the proof. It confirms that the cosmic dance of galaxies is real, and that the final violent union of their central black holes is not a rare exception, but a common, inevitable, and ongoing process across the sky. Furthermore, it powerfully addresses the long-standing final parsec problem. Theory had struggled to explain how two supermassive black holes after their host galaxies merge could lose enough energy to shrink their orbit from a few light years down to the point where gravitational waves could take over and finish the job. Some force, be it friction from surrounding gas or the slingshotting of nearby stars, had to bridge that final gap. The sheer strength, the loudness of this background signal tells us that nature has emphatically solved this problem. The universe is not quiet. It is roaring with the sound of these mergers, implying that the process for bringing them together is incredibly efficient. The cosmic engines at the hearts of galaxies do not stall. They roar to a spectacular finish, and now for the first time we can hear them doing it. The implications are breathtaking. We have, in effect, developed an entirely new sense with which to perceive reality. For all of human history, our knowledge of the universe has come from light, from photons captured by our eyes or our telescopes. We have been watching a silent movie. But gravitational waves are not light. They are vibrations in the geometry of space-time itself. They are not blocked or scattered by dust and gas. They travel unimpeded from the most violent and energetic events, carrying pristine information directly from the source. It is as if we have spent our entire existence deaf and have suddenly been granted the ability to hear. The sky will never be silent again. We have unveiled a new cosmic map, one traced not in light but in vibration. When we look out at the night sky, at the countless pinpricks of light that are distant galaxies, we must now understand that we are also looking at a sky filled with sound. From the direction of every one of those ancient island universes, a gravitational wave signal is likely on its way, contributing its unique voice to the cosmic choir. The signal we have found is the combined sound of that choir. It is a measure of the universe's total activity, a census of cosmic collisions writ large across the fabric of space-time. By studying the precise spectrum of this background hum, its loudness at different frequencies, we can begin to answer questions we once thought unanswerable. Are these mergers driven by gas-rich collisions, or the slower dance of stars? How do supermassive black holes co-evolve with their host galaxies? We can now perform galactic archaeology, not by looking at fossil starlight, but by listening to the echoes of the gravitational earthquakes that shaped them billions of years ago. This monumental discovery is not an endpoint. It is the dramatic opening of a door. We have pressed our ear to the cosmos and heard the indistinct murmur of a distant crowd. We have proven that the crowd is there and that it is vast and clamorous. We have confirmed that the universe is alive with the thunder of merging giants, a confirmation that fundamentally rewrites our picture of the cosmos from a static collection of objects to a dynamic, violent, and evolving entity. We have heard the ocean's roar, a sound that tells us more about the nature of the ocean as a whole than any single drop of water ever could. It is the loudest, most persistent sound in the universe, and we are finally, after all this time, beginning to listen. The achievement is a profoundly human one, a symphony of theoretical genius, engineering marvel, and decades of quiet collaborative dedication. It required looking at some of the most stable objects we know of, millisecond pulsars, to find evidence of the most cataclysmic events imaginable. It is a story of turning the cosmos into an instrument and learning how to play it. But now that we have heard this grand cosmic chorus, an even more tantalizing question arises. A new challenge for the next generation. Can we, from within this cacophony, ever hope to isolate the sound of a single voice? Can we pinpoint one specific pair of supermassive black holes and listen to their song alone, tracking them as they spiral toward their inevitable doom? And so the final cataclysmic wave of space-time distortion washes over us. The universe, for an infinitesimal fraction of a moment, holds its breath. What was once two separate monstrous singularities, each a point of infinite density, is now one. A new, more massive void has been born from the fury of their union, its freshly forged event horizon, settling into a perfect silent sphere. The echo of 1 trillion suns being unleashed fades into the background hum of the cosmos, a memory now imprinted not in light, but in the very geometry of existence. This is the silence that follows the loudest events in history. But it is not an empty silence. It is a silence filled with knowledge, with revelation, with the profound satisfaction of a journey that has taken us from the chalkboards of human genius to the very heart of galactic chaos. For a century, this was merely a whisper in an equation, a beautiful, almost fantastical prediction born from a single revolutionary mind that dared to imagine gravity not as a force, but as the curvature of a four-dimensional stage. Einstein gave us the language, the mathematics of a dynamic universe, but for decades, that universe remained stubbornly quiet. We looked out with our telescopes, our eyes tuned to the brilliant spectacle of light, and saw a cosmos of breathtaking beauty. Yet it was a silent film. We witnessed the waltz of galaxies, the birth of stars, the violent supernovae, but we could not hear the fundamental rhythm that drove it all. The search for these gravitational waves, was an act of audacious faith, a multi-generational quest to build an instrument of impossible sensitivity. We had to devise a way to measure a distortion in reality, smaller than the nucleus of an atom, across a path several kilometers long. It was a task akin to listening for a single pin drop in the middle of a hurricane, an endeavor so challenging many believed it would never succeed. Yet, we persisted. We built these giant L-shaped antennas, these incredible gravitational ears, and we waited straining to hear the faintest tremors from the depths of space and time. And then, on September 14th, 2015, the universe finally spoke. That first iconic chirp was not the roar of supermassive black holes, but the death spiral of two smaller stellar mass cousins. Yet in that fraction of a second, everything changed. A century of theoretical physics was proven true in a single rising tone. A new window, a new sense had been violently thrown open. We had spent all of human history staring at the sky, but for the first time we were finally listening to it. From that first detection, the floodgates opened. We began to hear a chorus of these smaller collisions, each one confirming our models, each one allowing us to refine our understanding of gravity in its most extreme form. But the true leviathans, the supermassive black holes we have journeyed with, remained tantalizingly out of reach. Their mergers, the galaxy-shaking events that punctuate cosmic history, were too slow, their frequencies too low for our ground-based detectors. We had to learn a new way to listen, to turn entire galaxies into our instruments, using the impeccable timing of pulsars as a celestial metronome. The discovery of the gravitational wave background, that gentle hum from the mergers of countless supermassive black holes over billions of years, was the next great leap. It was the confirmation we sought. The universe was not just punctuated by these violent crescendos, it is constantly simmering with their combined gravitational song. Looking back on this incredible path from a ripple in an equation to this tangible, all-pervading cosmic hum, we see now that our previous view was incomplete. We mistook these mergers for mere acts of cosmic demolition. We saw them as the final violent punctuation mark at the end of a galaxy's story, the ultimate manifestation of gravity's power to consume and to destroy. But we were wrong. These are not endings. They are the engines of cosmic creation. They are the architects of the universe we inhabit today. Every time two of these giants collide, they don't just create a larger black hole, they fundamentally reshape the galaxy around them. The colossal energy released in that final fraction of a second, more powerful than all the starlight in the observable universe combined, does not simply vanish. It slams into the surrounding galactic ecosystem like a thermonuclear shockwave. This blast of gravitational energy and the subsequent radiative feedback can blow the gas right out of a galaxy's core, halting a frantic era of star formation and preventing the galaxy from growing bloated and unstable. It acts as a cosmic regulator, a natural thermostat that ensures galaxies evolve in a balanced, structured way. Without these mergers, the elegant spiral arms of a galaxy like our own Milky Way might have never formed, instead remaining a chaotic, shapeless cloud of frantic starbursts. These collisions are the sculptors of galactic morphology. Furthermore, the merger process itself is a gravitational gyroscope for the host galaxy. As the two black holes spiral inward over millions of years, they stir the pot. They gravitationally eject stars from the galactic center, scattering them into wider orbits and puffing up the central bulge. They redistribute angular momentum, altering the spin and orientation of the entire structure. The grand elliptical galaxies we see, those ancient golden cities of stars, are themselves thought to be the product of multiple generations of such mergers. They are the serene, settled aftermath of a violent, chaotic past, their shape and structure a direct fossil record of the supermassive black hole collisions that forged them. And what of us? The very elements that make up our planet, our bodies, the iron in our blood were forged in the hearts of stars. But it is the grand cosmic cycle governed by these mergers that ensures those elements are distributed far and wide. The gravitational tides and energy blasts from these events can trigger new waves of star formation in the outer reaches of a galaxy, seeding fresh clouds of gas with the heavy elements created by previous generations of stars. They are an integral part of the universe's system of renewal and rebirth. So when you look up at the night sky at the serene river of the Milky Way, know that you are not seeing a quiet, peaceful kingdom. You are seeing a dynamic living structure, one whose present-day shape and very ability to foster life were profoundly influenced by the gravitational screams of ancient, monstrous collisions at its heart. This realization has gifted us more than just new knowledge. It has given us an entirely new perception of the universe itself. We are leaving the age of cosmic silence behind. Our old metaphor of the cosmos as a silent clockwork mechanism, a series of beautiful but mute images, is being replaced by a far more visceral reality. The universe is alive with sound. It is a place of vibration, of rhythm, of a constant, complex symphony played on the instrument of space-time itself. What we have heard so far are just the first few tantalizing notes. The high-pitched chirps from stellar mass collisions are the piccolos of the orchestra. The low, persistent hum of the background is the steady, resonant drone of the cellos. But the true titans, the supermassive black holes whose stories we have followed, they sing in a key all their own. They produce a sound so profound, a frequency so impossibly low, that a single wave can take minutes, hours, or even years to pass by. These are the bass notes of the universe, and to hear them to isolate the sound of a single supermassive merger from start to finish, we cannot listen from the noisy, shaking surface of our own planet. We must take to the ultimate silence of space itself. This is the breathtaking promise of what comes next, an observatory not of glass and steel but of laser light and pure distance. It is called LISA, the Laser Interferometer Space Antenna. It is an instrument of such audacious scale and ambition that it represents a leap in our observational capabilities, as significant as the invention of the telescope. Imagine, if you will, not 2 but 3 separate spacecraft flying in a perfect triangular formation, a celestial triangle, millions of kilometers on each side. They will trail the Earth in its orbit around the Sun, a silent, graceful dance in the vacuum of the solar system. Between each of these spacecraft, a laser beam will be constantly transmitted, received, and sent back, creating 3 colossal arms for an interferometer vastly larger than anything we could ever build on Earth. The mission of these 3 spacecraft is to do one thing with unimaginable precision: measure the distance between each other. They must maintain their formation and track their separation with an accuracy so extreme it staggers the imagination. They will be looking for changes in distance of just a few picometers, a tiny fraction of the width of a single atom across a gulf of millions of kilometers. The engineering required to achieve this is nothing short of miraculous. Each spacecraft must be a gravitational sanctuary protecting a small, free-floating cube of gold-platinum alloy from every conceivable disturbance. The gentle pressure of sunlight, the subtle buffeting of the solar wind, even the heat radiating from the spacecraft's own electronics, all of these forces must be perfectly counteracted by microthrusters to ensure that the test masses are influenced by only one thing: the pure, clean curvature of space-time. LISA is a cosmic hearing aid designed specifically to tune out the high-frequency noise of our terrestrial world and listen for the deep infrasound rumble of the true giants. With this incredible instrument, we will finally hear them. We won't just detect the final moments of a merger, we will be able to hear the entire courtship. We will tune in years before the final collision, listening as 2 supermassive black holes begin their slow, inexorable spiral. We will hear the sound of their orbit tightening, the frequency of the waves slowly rising as they shed orbital energy, a slow, patient crescendo building over months and years. This will allow us to map their dance with exquisite detail. We will be able to measure their masses, their spins, how they are oriented in space, and even the subtle wobbles and eccentricities of their orbits. We will be testing Albert Einstein's theory of general relativity in a gravitational regime of unimaginable violence and power, a place where space-time is being twisted and warped to its absolute breaking point. Any deviation, any unexpected quaver in the song of their merger could be the first hint of a new, more complete theory of gravity, a crack in the foundations of modern physics that could lead to a revolution in our understanding of reality. But the promise of LISA extends even further into the deepest questions of our cosmic origins. With its unparalleled sensitivity at low frequencies, LISA will be able to hear the whispers from the very dawn of time. It will detect the mergers of the first seed black holes in the infant universe, the collisions that took place when the cosmos was just a few 100 million years old. These are events that are completely invisible to our light-based telescopes, shrouded in the thick gas and dust of the first galaxies. LISA will bypass light entirely. It will hear the gravitational echoes of these primordial mergers, allowing us to create the first maps of how the very first cosmic titans were assembled. We will be doing a form of gravitational archaeology, uncovering the history of cosmic structure, not by what we see, but by what we hear. It might even be able to detect gravitational waves from even earlier epochs, perhaps from the inflationary period, just a trillionth of a trillionth of a trillionth of a second after the Big Bang itself. Such a detection would be the ultimate prize in cosmology, a direct signal from the moment of creation, a baby picture of the universe, not in light, but in the vibrations of its birth. This is the future that awaits us. A future where we map the unseen universe, where we chart the dark side of the cosmos through its gravitational symphony. We will track the mergers of supermassive black holes across cosmic time, witnessing firsthand how they build the galaxies we see today. We will probe the nature of dark matter and dark energy by observing how they influence the propagation of gravitational waves across billions of light years. We will ask whether black holes truly have no hair, whether their event horizons are the perfect simple surfaces predicted by theory or something far stranger. We will listen for the unexpected, for the sounds the universe makes that we haven't even conceived of yet. For if the past has taught us anything, it is that every time we open a new window onto the cosmos, what we find is more wonderful, more complex, and more surprising than we could ever have imagined. We stand on the precipice of a new era of discovery. The journey from a thought experiment to a sky filled with song has been a long one, driven by that most fundamental of human impulses, the need to understand, the need to know our place in the grand scheme of things. We have learned that the universe is not a silent, static painting. It is a dynamic, evolving, and profoundly noisy place. It is a cosmic orchestra, playing a composition of unimaginable complexity and timescale, one filled with violent crescendos and deep, resonant drones. The story of the universe, it turns out, is not written in starlight. It is sung in the key of gravity, and we, after an eternity of silence, have finally learned to listen. The symphony is just beginning.